Good afternoon, everyone. Welcome to the post-lunchtime session. My name is Pamela O'Shea. I'm on the Black Hat Review Board for Asia, and it's my absolute privilege to introduce you to our next session, Dismantling the CEOS Protocol. I'd like to introduce both our speakers. We've got Iceman, who's co-founder of AuroraSec, or ORG, and Adam Foster, who's senior pen tester at Onestep Group. Join me and welcome to the stage.
Thank you. Hello and welcome. So let's get started. Presentation, Dismantling CEOS Protocol. As said, I'm evildaemond, this is Iceman, and we'll do a quick intro. This is me, this is how you pronounce my handle. This is a fight that I've had ongoing. It's evildaemond. I work as a senior penetration tester by day. I've spent like 10 years in InfoSec at this stage, and a lot of it I teach physical security for people. On top of that, I specialize in electronics and hardware, and that's where a lot of people know me from.
So I'm Iceman, and I've been hacking RFID systems for over a decade. That's a very loud mic. I can hear my voice. That's a bad sign. I love open source, and I use 4 spaces instead of a tab. I don't know why I say that, because I love that. Anyway, let's get on.
All right, so we're going to talk about why we do this. So if you don't know about this, this is CEOS. I got these cards when I bought an access control system. Don't ask why I'm buying access control systems. They're fun. But there was no substantial information online, and there was a lot of people saying, it's secure. And people want to know how things work, so that's what we're focused on. So at the end of the day, this talk is all about 3 things. Understanding how the system works, reviewing what the system actually uses, and then understanding the security of it. Because at the end of the day, that's most of it. But we're also very, very careful about this because a lot of people might not know how RFID works. So here's Iceman with a 101 on RFID.
For you guys who don't know what RFID is, it stands for radio frequency identification. And it basically works like this. You have a tag and you have a reader. Inside of a tag, you have an inductive coil that charges up a capacitor and powers on an IC. The IC might or may not have little memory or more memory. And that is then, when presented to an RF field that the reader generates, starts communicating. Now, the old way of doing this is simple. It's just the reader saying, send me the content of X. The reader goes, here you go. It could be a facility code and card number. And you get a green light, if that was okay. And if you did it again and you send the wrong code to it, you will get a red light. That is super simple. Now, in order to replay that, the evil PAX guy can come and go and sniff that because there's no encryption. It's just plain text over the wireless. The reader says, send me content X, and the PAX guy just sends what he's stolen. And he gets a green light. Now, in order to handle that, they started to protect it a little bit more with passwords. So the reader starts saying, no, give me the content X, but use the password lemon. And the tag goes and gives it the memory. The evil PAX guy can now try to say that, and when he answers it, what's the password? Soups. He doesn't get in. Quite simple. And the next step to negotiate that is to use encryption. And then it starts looking like this. Reader asks for gobbledygook. Tag answers back with gobbledygook. And then it says, yay, okay. That leads us to this talk. And this talk is about the CEOS, but uses a lot of that gobbledygook. And we're going to make that a little bit simpler for you.
So, quick run through. This is not a CEOS tag, this is a black box with some white text on it. But in general, CEOS is also known as I-class CEOS. It's produced by a company called HID Global, and it's a successor to their previous I-class generation. There was some information publicly about it. It's mostly in white papers and similar, mostly saying strong authentication, heightened privacy, AES encryption, all the really good buzzwords that we all love to hear. But it's also a lot of discussion about it's going to be future-proof and make everything more secure. But the documentation wasn't great. There's not much online, and it mostly boils down to white papers. So we're going to run through a couple of terms. These are going to pop up a couple of times. Just chuck these in your memory. They'll appear. Cool. 3, 2, 1. Hope you caught it in your brain. So When we break down a CEOS tag, there's a GDF, which is like the management side of things. This is like the overarching controller. Then a couple of ADFs inside. ADFs are what actually contain the data that you care about. And you'll have them in flexible stores like this. They'll be represented by an object ID. So we're just using a hexadecimal representation here with a couple of data objects inside of there. Those data objects will also have keys associated. So you'll have a privacy key, a MAC key, and some authentication keys that allow you to do different things, like say, okay, we want to authenticate to this and write data, so it might use a different key from when you read data. Good segmentation overall. And that means you can also have different objects, and those objects, individually, can be accessed with different keys. It's great. But that means we're going to look at this diagram and go, what's this? What's this stuff happening in the middle? So that brings us to, how do you reverse engineer an RFID protocol? I got no idea. But you kind of have to figure it out. A lot of public sources, stuff like their public documentation, a little bit of patent information because it's useful to know about. They're going to publish patents if they want to secure their stuff. A couple of academic papers which helped a lot. And HF14 sniff A is, well, 14A sniff on the Proxmark just gets you some good information. But that information looks like this. And I don't want to put you through looking at this for the rest of the talk. Because I did. And oh boy, my eyes hurt afterwards. So I'm going to be really nice and break it down. So each part of this is going to represent a frame of communication, or part of it is just back and forth. So what do we have first? We have this. This is a basic APDU command. It gets encapsulated at the start with a 0B, 0A. Then you have the actual command itself, which is the APDU. And then the CRC, which is just a checksum saying, hey, this data that we sent is correct and you didn't break it halfway through. In this case, this is the ISO 7816 select file command. ISO standards for this are really public and nice and easy to read. But the idea of it is that it selects an application on the card to say, this is what we're going to use. In this case, this is the application ID. And that's a mixture of what's referred to as the RID, the registered ID, and the PICs. So we start with the application, and in a response, we see the APDU response, a response of 90 and 00, which is just saying, okay, we're good. And we get a data response, which looks like this. So from there, we get our first interesting command. This is our get ADF command. This isn't really standardized and really kind of had to just whack it together. I couldn't find much documentation online either, so my guess is it's custom. So we're just going to call it get ADF. We've also seen it used for other things, such as the GDF, but it breaks down to an instruction header, which is the A5, and 04 is just saying we want to get the ADF for this object ID. Modifying from 04 to 07 has been seen in a couple of sniffs when doing writing of cards, but I don't know how that works. And then you send the rest of the command, which looks like this, which is ASN1. To make your life easier, ASN1, just think of it as tag, length, value. I put the length in brackets just to make life easier. And you have the object ID there, which is what you're referencing. And yeah, that's the decimal representation in this case. From there, you get a nice response, looks like this, 9000, all good. And we get a response like this, which is broken down ASN1. Though this again sucks. So here's our encryption hash algorithms. That's the first part of this, saying we're going to communicate in this format. So when you do hashing, please use this. When you use encryption, please use this. Then we have the cryptogram, the thing that's encrypted with the key from our privacy key slot. And finally, we have a MAC, just verifying this is the right one, and that uses a different key altogether. So you decrypt that with whatever key you have, and out comes the OID and the diversifier. The diversifier is the first thing you actually care about because it's used later on to encrypt the key properly, but that's used by the reader. So when we think about the representation of how they're doing security, think of it this way. It's the first layer inside. Then we move on to the next part, and this is ISO 7816 general authentication. for people who don't read documentation for a living and don't hate their eyes, the best way to think about this is it's a way of securing communication. Yeah, secure messaging is the actual name, but no one cares about that. This is the first command, it's general authentication. And you'll see we're using 01 as our key slot, saying this is the key we're going to use, and the type of instruction. In this case, we're trying to get what we're calling the R&D ICC, or random ICC. And authentication key slots from what we've seen go from 00 through to 0F. Now, in a response, we get a value like this again, makes life easy, break it down to the ASN1, we get the R&D ICC value. As a fun note, this appears static across some cards. In documentation I've released for the Proxmark, it's referred to as a static nonce. That's incorrect. But we're just going to call it R&D ICC here. This can be changed in a flag from what we can see, but... And then we get a response like this, which is our general authentication. This is what we're going to use to make sure everything's secure. And of course, when you break it down, it's long bytes and then some MAC. What's actually happening here is they're taking the ICC value that it got from the first challenge command, putting a random IFD value and a key IFD value, whack it all together with our diversified encryption key, and then pipe it back out as a cryptogram, which just makes it easy to decrypt. And when the tag does it, they go the opposite way. Just shove it through the diversified key and get the same values out. And then we see the exact same thing again. We go through and we send the same cryptogram and MAC, except for we're going the opposite way around. So we're going to get a new value of the key ICC. Same thing, diversified key, already written on the tag, and then pipes it out. Then the reader does the same thing, shoves it through a diversified key function, out comes our new key ICC value. And this is the next layer. It makes your life a lot easier when you see it in layers like this. And finally, we actually get to the first thing that matters here. This is the get data command. This is ISO standard, makes life really easy to look up data on this. It's using secure messaging, so what we'll see here is a couple of tags. And they're a cryptogram and a MAC. You can look up the ISO standards, makes life really easy here compared to some of the others. And from there, what happens? Oh, we have to create the key. So because we're using secure messaging and we have to assume that the privacy key, the read key, whatever key you're using that's encrypted, all of that has to be sent over secure communication to make sure that it's all safe and sent. All these values come from that, and then that gets shoved into a hashing algorithm and generates the secure messaging. So this is our keys for the encryption and the MAC. Now, this is where we use MAC chaining, where the idea is that each sequential command gets incremented by 1 when you add the MAC together, meaning that when you actually send the data, we're making sure that the sequence of data being sent is correct as well. So that gets shoved into the secure messaging MAC key, and then you can verify, yep, the MAC's right. And then when we do the command encryption, we don't have to do any magical stuff with MAC chaining. We just shove the secure messaging encryption key in, and out comes our encrypted command. And this is what you would normally see, something like 5C and then D0. So this is a request to get the object in data 0.0 or D0, and we get the padding, which just pads it out from there. And then we get our command response. Again, from here, we get a 90 OK. So we're all good on our response. And we get a beautiful, beautiful ASN1 blob like this. And what's inside? Same thing, cryptogram. We get a new ASN1 tag response code. Don't ask why they're using 2 response codes. I would love to know. If you know, please tell me. It has driven me insane reading through trace files. And then the MAC saying this is the right value. Same thing as before, but we're just incrementing the random value by 2 instead. Shove it through the secure MAC, and we're good. And decrypt the command, shove it through the same encryption key, and now we get our decrypted response. And same as before, we're just looking at an ASN1 tag with the object data coming in. And then it's all padded out just so that the block size is proper for the encryption. So it all looks like this to actually get the secure data out of there. So each layer is another protection mechanism over the top. And the best way to think about this is an onion or an ogre. They have layers. And yeah, that's the best way to start from this. And now on to Iceman. He's talking about another part.
Take a little break so you like feel the number of bytes, slowly get into yourself and like take a breather. Take a small breather. Because I'm going to hit you with this. We're going to talk about the secure identity object. This is called the SIO. If you're into this world of access control systems, you're going to hear that a lot of times. The SIO is what you can see like a container of things. It's like an object where you push things in. And you can store it everywhere. So it's like carrier independent. So you can store it on an RFID card. You can store it on your secure element on your mobile phone. And you can transmit it over any kind of carrier. Doesn't matter. What it has is encrypted and signed payloads inside. It uses diversified keys for those payloads. And it's also variable size. So it's a very practical format that we made. Did that all make sense? You're just tired already. I can tell. This is how it looks. More bytes? Yeah, I know. We're just going to go through slowly. I'm going to show you how it looks like in ASN1 instead. This is how it looks like. Much easier, doesn't it? When you look at it a little bit more, I'm going to point out the important parts, which you see now in green. And it starts to make more sense, doesn't it? Let's go through them. Let's break it down. First of all, you got the relative OID. You got the key reference ID, and you got the crypto. And finally, you got the PAX payload, the encrypted PAX payload. Let's break down all of this stuff when we have taken them out of context. Oops, too fast. Every SIO belongs to a root ID, OID. So you just tag that onto it, the relative OID. Every key reference indicates what kind of key set was used to encode or encrypt this SIO. So if it's a 1, it means that you use the standard keys. Or if it's 0, 0, what I heard right now is elite keys, and I haven't had access to a custom keyed SIO, so I can't tell what that one is. I also know that the elite SIOs looks a little bit different from this one. But we're going to talk about standard ones. Cryptos. SIO can use 2 different cryptos, the EIX and EIX prime. They're denoted here by 030008 or 09. And finally, the PAX payload. And that contains 2 parts. It's not obvious when you see it like that, because it's not T-value encoded. So remember when I said it's variable sized? The signature part of this payload is always 16 bytes in the end, and the rest in front of it is the encrypted payload. And that can variable in size. In order to decrypt the payload, you need a key. And every SIO uses a diversified key. We like diversified keys. It's good. For that, you use a KDF. That's what we call a key diversification function. And my game, back in the days, we call it keygen, key generation. I'm not going to talk so much about how that one works, but behind the scenes, it uses AMAC with SHA-1. And you feed it a very special crafted 48-byte input. And that generates a 16-byte output. Now, for you guys who program in a memory unsafe environment like I do, remember that the AMAC uses or creates a 20-byte hash. You don't want that buffer overflow, trust me. So you got the diversified key, you got the encrypted payload. Now what? Time to look at the next layer, the crypto algorithms. So SIOs uses something, and this is such a mouthful. This is called Authenticated Encryption with Associated Data, AEAD. I'm not going to say that more once in this talk. So what you get is encryption and signature in one go. And behind the scenes it uses AES and OMAX. They use 2 different AEID cryptographic algorithms, the EIX and EIX prime. And in order to find these academic papers, you figure it out and go back 2010, 2005, I said academic papers about these ones. And the EIX is now implemented in Python libraries and stuff like that. So I didn't know that. Well, I would have helped before we did this, but now it is like that. It has the variable size of encryption byte and always generates 16 bytes of signature. The AIX Prime is another version that uses for the GSM traffic, among others. They use AES in CBC mode, CMAC. It uses X variable number of encryption bytes, and a little bonus, it uses variable number of signature. The standard defines it as 4 bytes, but the CO uses 16 bytes. And when you look at this and you realize, hey, I need to implement this. And HID uses the bouncy castle C implementation, which is open source. Good for us. But I needed a C implementation. And that took me 2 weeks of painfully trying to implement 2 different cryptos from academic papers. To get even test vectors was just awful. Because it took me such a long time to understand that all those vectors they had and their implementation was made in big endian, whilst the C implementation I was looking at was doing it in little endian, meaning my test vectors were completely useless. Finally, I got around and made it happen. So what happens? You got the crypto in order to do that. So you take the payloads things that you want to shove it in, you take the diversified key you generated before, you stop it and put that into the AIX or AIX Prime, and out comes the decrypted data together with the signature OK. It can also give you a signature not OK, so you need to check that one. And now we go to the next layer. We'll take a little breather here, to just, it's too much data. I know. It was awful for us too when we did this. We're going to look at the next thing. When you decode this one here, they use something that's called padded PAX Wiegand format. It's another mouthful piece of things to say. What it is that it's instead of Wiegand formats, usually you see the raw Wiegand in hexadecimal. This one here has the first byte indicates the number of bits of zeros that it needs to shift. So if you take a sample, this is just a random sample. So we take the most common format that's out there. This is H10301. It's a 26-bit PAX, and it looks like this: 06, 1B, 7D, 0040. Now, 06 is the number of bits that need to shift, and the rest is the PAX payload. And we take it out like this. We convert it into binary because it pushes the message a little bit better. So what we want to do is take those 6 bytes in the end and want to shift that 6 times. Now we take that number and we want to have the exact binary string as it is because we want exactly 26 bits. And we put that into a Wiegand decoder. Luckily, the Proxmark client does have one of those commands that actually accepts the Wiegand in binary. And out comes the decoder facility code and card number. Now, when you see here, the observant ones of you guys sees this immediately that, hey, Iceman, there's 2 formats. Yes, there are thousands of Wiegand formats out there, and it can be custom made, and it's just different. And what you see is you have 26 bits, and if you have known 26 bits length of PAX formats, you just push that into the decoder and see what comes out. If the parity says OK, that usually is OK, but now we have both an Indala version and a H10301 bit. But by number of generality, number of the masses, it's going to be the HID ones. So we took the PAX padded format, we decoded, we decrypted. When we expressed it in Wiegand format, that would be facility code 54 and card number 64000. And that's the peel onion. That is the whole shaboom of going from one end to the other end of the secure information. So what are our thoughts about this one, Evil?
Yeah, well, honestly, I'm going to be straightforward. It's a pretty damn secure system. I like it. and they put a lot of thought into the system. If you know the history of HID, they've had issues in the past, and this is a lot of adopted open standards, a lot of good security being managed, and it's really well done. And this is definitely not a talk about things being broken. This is just talking about trying to make things better for everyone. Systems like this need independent testing. They're used for everything from critical infrastructure all the way down to your local mum and pop shop. And vendors should be embracing this type of research. We want to see vendors come through and say, hey, we like this. Here's the information publicly. Help us figure out, is it secure or not? And so if you take anything out of this, review how systems work. The white papers don't tell you everything. Evaluate it beyond just a data sheet. Look at how it works deep. And if you actually find a vulnerability, go report it to the vendors so that it gets fixed. And thank you. It's been a wonderful Black Hat Asia, and yeah, we're happy to be here.
Well, we got some time over, so we can take a question Q&A.
Yeah.
Any questions? The room is silent. There was too many bites. Full research?
Like 6 months-ish, we've been working on it for.
6 months-ish, yeah.
Something like that.
Something like that. Well, it depends how you see it. You know, it's spread out over years. I mean, I first looked at SIOs and SEOs 2016. It's been sprinkled across the Proxmox forum over the years. So yeah, but for this, it was about 4 or 6 months.
Yeah, something like that.
Any other questions?
Well, always happy to take questions afterwards if people want to ask. But thank you, and enjoy the rest of your Black Hat.